Random variable is a numerical measure of the outcome from a probability experiment, so its value is determined by chance. Random variables are denoted using letters such as x. So these are variables just like you would have talked about in algebra, x, y, z, and so on. The variable has a single value for each outcome of a probability experiment. And a discrete random variable has either a finite or a countable number of values. Earlier in this class we talked about discrete data versus continuous data. We also have the same distinction with random variables. We can have discrete random variables and continuous random variables. So remember that discrete data talks about something being countable. Countable refers to the fact that there might be an infinite number of values, but they result from a counting process. The values can be plotted as points on a number line with spaces between the points. So remember, there are gaps between the values. Here's some examples of probability experiments and the discrete random variables that would go with them. So one probability experiment would be rolling a die. The sample space, in other words, the set of outcomes for what comes up on the die, are the numbers 1 through 6. So for this one, our discrete random variable x would have possible values of the whole numbers 1 through 6. Another experiment would be selecting a part and inspecting it. Now the possible outcomes for this experiment would be either that the part's defective or that it's not defective. Now when we're defining a discrete random variable, we have to give it numerical values. So we would have to define some numerical values to represent defective and not defective. One way this is done a lot of times is using 1 for one of the values and 0 for the other value. So one way we could define a discrete random variable for this probability experiment would be to define defective as the value 1 and not defective as the value 0. Another experiment we could do would be to play a game where one playing card is drawn from a deck and the player wins or loses money depending on the suit of the card drawn. So the possible outcomes when you draw a card from the deck and only look at the suit are the 4 suits: hearts, diamonds, clubs, and spades. Now again, to define a discrete random variable, we have to give those outcomes numerical values. So if we're playing a game and we're winning or losing money depending on the suit, then we could assign each suit with the amount of money that we would win or lose if we drew a card in that suit. So here's some possible values for x. For example, if we won $2 if we drew a heart or a diamond, then those would be the numerical values for those two outcomes. If we won $3 by drawing a club, that would be the numerical outcome for that outcome. And if we lost $8 if we drew a spade, then we would make our x value -8 to signify that we lost money. One more experiment is drawing 5 M&Ms from a bag with replacement and recording the number of red M&Ms drawn. So our possible values for our outcomes are just the total number of red M&Ms that we drew out of the 5. So we could have gotten anywhere from 0 red M&Ms all the way up to 5. So that is our sample space, and we can define our discrete random variable as having any one of those values. Now let's look at some examples of discrete probability distributions. If you remember in Chapter 5 when we talked about probabilities, we did talk about probability distributions. And all we did was create a table that had the list of outcomes in one column and the probability for each outcome in the second column. Again, a discrete random variable has to have a numerical value. So when we're creating a discrete probability distribution, we have to list the variable such as x and its numerical values. So for the experiment of rolling a die, this is what our probability distribution would look like. So we have x, which is our random variable, in one column, and the other column is the probability for each value of x. So our possible outcomes for rolling a die, our numerical outcomes, are the values 1 through 6, and here's the probability for each different outcome. Since each of those values is equally likely to come up on the die, the probability for each one is 1/6. So this would be our discrete probability distribution for that experiment. Now for the experiment of selecting a part and inspecting it, we have to know a little bit more in order to create our probability distribution. So for this experiment, let's suppose that 8% of the parts produced are actually defective. So here's what our probability distribution would look like. Now we can list the outcomes in words over here, but they're not technically part of our probability distribution. Our probability distribution is really these two columns where we have the variable and its numerical values, and then the probabilities for each value of the variable. So in this case, if 8% of our parts are actually defective, then the probability of the part we select being defective is 8%, or 0.08. And we decided to give defective the value 1, so here's the value of our variable and here's the probability for that value. If the part's not defective, we gave that a value of 0, and the probability of it not being defective would be 92%, or 0.92. Now there are two conditions for something to be a valid probability distribution. First, the probabilities all have to be valid probability values, so they all have to be between 0 and 1. We can't have any negative probabilities, and we can't have any probabilities that are greater than 1 or 100%. The other condition is that the sum of the probabilities in our distribution has to be 1. So if we add up all the probabilities in our table, they have to add up to 1 or to 100% if we're listing them as percentages. Now let's look at an example of discrete probabilities in general. And this is the same experiment that we talked about earlier, where we play a game where one card is drawn from a 52 card deck. If the card is a heart or a diamond, you win $2. For a club, you win $3. For a spade, you lose $8. So what's the probability that you win money on one play? What's the probability that you win more than $2 on one play? And what's the probability that you lose money? First, we're going to construct the probability distribution table for this game. And remember the two conditions that we just talked about. The probabilities have to be between 0 and 1, and the sum of the probabilities has to be 1. So here are our outcomes in words. We can list hearts and diamonds in the same row because they have the same numerical outcome. For either one of those, you win $2. Clubs has a different outcome, that's that you win $3, and spades has another different outcome in that you lose $8. So for our numerical outcomes, we're going to use the amount of money won or lost, and if it's a case where you're losing money, we're going to make that a negative number. So our numerical outcomes would be 2, 3, and -8. The probabilities, since there are the 4 different suits and an equal number of cards in each suit, then the probability for each different suit is 1/4. So here, since we have 2 suits combined, the probability there would be 1/4 plus 1/4. For the other 2 suits, each one of them has a probability of 1/4. So here's our final probability distribution. We have our numerical outcomes here, and here we have our probabilities. It's 1/2 for a heart or a diamond, 1/4 for a club, and 1/4 for a spade. And just to check that we've computed these probabilities correctly, we can add them up and they do add up to 1. So now that we have our probability distribution table, we can easily answer these questions. So what's the probability that you win money on one play? Well, you'll win money if you draw either a heart, a diamond, or a club. So these are these two numerical outcomes, either a +2 or a +3. And to get the total probability, we can just add those two values together. So the probability of this would be 1/2 plus 1/4, which is equal to 3/4 or 0.75. What's the probability that you win more than $2 on one play? Well, you will win more than $2 only if you draw a club. That's only this outcome, so the probability is just going to be 1/4 or 0.25. And finally, what's the probability that you lose money? You'll lose money if you draw a spade, so the probability again is 1/4 or 0.25. Now notice that this is also the complement of winning money. You're either going to win money or you're going to lose money in this game. So losing money is the complement of winning money. We already found the probability of winning money was 3/4 or 0.75. So we could find this probability by subtracting that value from 1, and we'd get the same answer as we got by finding the probability directly.